So thank you so much for the kind intro, and it's really an honor to be here on stage at Republica with such luminaries like Alexander Gerste, the astronaut we heard speak earlier, Cory Doctorow. It's a pleasure to talk to you today about some of the great mysteries of the universe. And I'm going to be talking to you about simulating the universe. And I honestly find that a little bit less scary than giving a talk today on stage following some of the greats. So I'm going to start out by just giving you a little overview of our best understanding of the universe as it is. And this, in astrophysics, we call the Concordance Cosmology. Basically, our agreement as to the best description of the cosmology that we have today. Now, what is cosmology? Well, cosmology is the science theory of the universe as an ordered whole and of the general laws which govern it. And our concordance cosmology incorporates general relativity, the Big Bang and expansion, inflation, and cold dark matter, as well as a cosmological constant. And by the end of this talk, you'll be able to describe at a cocktail party many of these things. And here's a little diagram of the history of the universe. So we have the Big Bang, then quantum fluctuations grow via inflation to a cosmic scale. And this provides the seeds of structure that we see today. And we have, in fact, a photo, a baby photo of the universe about 300,000 years after the Big Bang. In this diagram, that's that afterglow light pattern. And we can actually see the matter distribution at the beginning of the universe. Then things are a little bit dark until the first stars begin to form from those overdensities in the early universe. And these stars come together in a hierarchical fashion, dark matter clumps merging, and we'll see this in the simulation later, until we get galaxies themselves and later clusters of galaxies. And in the late time, at the present day, we actually see not only an expansion of the universe coming from the Big Bang itself, but an accelerated expansion, which we'll see later that we explain by this cosmological constant. So when I get to actually simulating the universe, something important to remember from this picture is that to simulate the universe, you need some place to start from. And the initial conditions we actually take are from this baby photo, the cosmic microwave background radiation. Those are the initial conditions for our simulations. And then we can evolve these forward with our best physical models to actually see galaxies themselves move and structure form in a way that we as human beings wouldn't be able to otherwise in our small, short existence. And we're able to observe the universe with telescopes and compare our simulations to actual observations and refine our understanding as well as motivate and show those people who are actually doing the hard work of observing or analyzing data from telescopes where and what they should be looking for. So let's start out where the universe did with the Big Bang. And the Big Bang was first observed by Hubble, or theorized by Hubble, when he observed that galaxies farther from us were receding faster from us, which, if you trace this back in time, puts galaxies closer together and leads us to infer that things were closer in the past and now are moving apart from each other. In addition, this baby photo that I'll keep on going back to, the cosmic microwave background radiation was discovered in the 50s in a radio telescope out at Bell Labs by a couple of radio astronomers who weren't looking for this at all. And they saw a noise in their radio telescope, which at first they blamed on pigeons. And I actually got to hear this story from one of the Nobel Prize winners, later a Nobel Prize winner, about how after the pigeons were taken away and the noise still existed, they realized that this could actually be a physical phenomenon. They consulted some theorists at Princeton, and the theorists said, well, actually, we predict this. And then later, this was observed in very great detail with several satellites, first WMAP and later Planck, and we actually can see that for a large part, this original part of the universe was homogeneous and isotropic. That is, it looks the same in every direction, and we theorize because we don't think that we on the Earth or in the Milky Way are in a particularly special place in the universe, that it probably looks the same on every patch of the sky. And in fact, this matches very well with observations to parts in almost a million. And if you actually look at a blown-up version of this photo, you'll see that if I accentuate the differences, scientists actually observe some large-scale correlations. That is, large regions that actually have some causal connectivity to each other. And small fluctuations. That is, it's not all the same color. There are small differences. And if the universe was small and everything had enough time to come into thermal equilibrium, then there would be no structure at this point. It would be all the same temperature. It would be all the same density. However, we theorize, because of quantum mechanics, that in the very early stages of the universe, fractions of fractions of fractions of fractions of a second after the Big Bang, the universe was small enough that quantum physics would still dominate. And at the quantum scale, things are weird, as I'm sure you've heard, and there are fluctuations, there are differences that are coming into account because of quantum effects. And because we see these large-scale correlations, if we didn't have something to blow the universe up faster than it might otherwise, these correlations would not exist, because essentially, if you were to calculate the speed of light, these areas of the sky wouldn't have had enough time at that point to have come into causal contact. So due to this and many other reasons, a physicist, Alan Guth, one of my former professors at MIT, theorized that there was this epoch that we call inflation, that in the very earliest universe blew the universe up to a cosmic scale at a much faster rate than one would expect otherwise. And this also solved several other puzzles, theoretical puzzles in cosmology, namely the horizon and the flatness problem. Essentially, how these large-scale correlations came to exist and how the universe is as flat as we observe it to be today. And so as I was saying, now we can see in pictures, quantum fluctuations are grown to a cosmic scale, and these fluctuations are exactly those that later incorporate overdensities that evolve into structure, that is, stars, galaxies, clusters of galaxies that we see today. OK, so the next picture of the concordance cosmology, the next piece of the puzzle, is general relativity. So our understanding of gravitational physics in the modern era started out with Newton and was refined by Einstein in a way that says that space-time tells matter how to move, and matter tells space-time how to curve. Einstein in 1916 discovered that while Newtonian physics describes our everyday regime at very high energies, high masses, extreme regimes, the theory was a bit more refined. And we have these equations, which look a little bit complicated, but it's basically writing out in mathematics what I said in words. On the left-hand side, we have space-time telling matter how to move. And on the right-hand side, we have matter telling space-time how to curve. And that equal sign is telling in that phrase. So essentially, if you change one, you get a change in the other. This is observed actually in, let's go back, sorry about that. This is observed in a phenomenon called gravitational lensing, where we can actually see this on the sky, this extremely theoretical concept of a relationship between space-time and energy. Essentially, we have here a galaxy cluster that actually bends light. It tells matter, light, how to move. And we can observe these lensed objects on the sky and calculate from that lensing the mass, the intervening mass. So let's move on to the final portion of the puzzle. One of the last things we need to understand the basic ingredients to do a simulation of the universe, and then I'll go into some unresolved questions as well, because if we knew everything about the universe, there would be no need to try to discover more. So cold dark matter was first theorized by Fritz Zwicky, who's actually a Swiss astronomer who migrated to Caltech in later days. And Fritz Zwicky observed that in particular galaxy clusters of nebula, in his day it was unclear that these objects called nebula were also galaxies, that the velocity on the outskirts of the cluster was higher than was expected, given our understanding of gravitational physics. And this phenomenon was noticed by Zwicky, and he theorized that there was some extended element of dark matter, of non-luminous material that was causing this. And with those calculations, he was able to predict how much of that intervening material there would be, as well as the velocity. And his predictions matched observations. And this kind of went by the wayside for some years until Vera Rubin and Ford in 1970 saw the same phenomenon in the Andromeda Nebula. And Rubin and Ford saw the same thing. On the outskirts of a galaxy, this particular one being Andromeda, the velocity was much higher than you would expect, calculating the mass from the light alone. And the idea of dark matter was further confirmed by one of the first examples of a simulation being used effectively to, in tandem with theory and observation, refine our understanding. And Ostraker and Peebles did an n-body simulation of a galaxy, essentially simulating it with and without some dark matter component. And without the dark matter component, they got things which didn't match observations, galaxies that weren't stable, as we observe. So here's one example from the plot of Rubin and Ford. I'll show you a few plots throughout this talk, but just to give you an idea of the type of data that we're actually dealing with, here we have velocity on the y-axis, we have radius on the x-axis, and we can see a very flat curve here. If there was not dark matter, what one would expect is this drop at the outer radius. And that's not, in fact, what we observe in modern galaxy clusters with modern observations. This is well matched, and this is an observation of large-scale structure. And body simulations showed these filamentary elements which formed. And this prediction from gravitational and body simulations matched very well observations from large-scale structure surveys. Additional evidence came from gravitational lensing, where you can compute the lensing of light and infer the matter map from that and compute the amount of luminous matter versus dark material. And again, this showed the need for some dark component. Finally, some evidence. There are many more pieces, but the last piece I'll present to you today is recent observations of a pair of colliding galaxies in what is called the Bullet cluster. And it incorporates smoking gun evidence for dark matter. Namely, we have X-rays from gas, that is luminous material, does not match the gravitational map from the dark matter. So we can see that there are two different medium that are interacting directly from observation. Finally, in recent years, and this was also recently awarded the Nobel Prize, there's a concept of a cosmological constant as an explanation for observations that began in the late 80s that have shown that our universe is not only expanding, but it's accelerating in its expansion, as I alluded to before. And essentially, you can observe remote supernova explosions, and particularly a type of supernova, type 1a, have a very regular explosion pattern. And you can precisely infer, very precisely infer the distance at which these explosions occur. And we've observed several of these, a suite of these in the modern era. And with these distances, with the explosions, with the ages of the stars, we can infer the expansion rate of the universe and show that it is, in fact, not only expanding, but accelerating in its expansion. We can as well predict from the cosmic microwave background radiation that the universe, the geometry of it, connecting the geometry of space-time to how matter functions in the universe, is flat, and calculate the amount of matter or energy that would be necessary to create such a flat universe, and realize that there's a bit missing. So these two came together in a neat explanation for what could be causing the accelerated expansion of the universe, namely the cosmological constant. That is, in those complicated equations that I showed you before relating the geometry of space-time to matter or energy, there's a freedom to add an additional constant term. And Einstein originally played around with this. These equations aren't given to us by some deity, they're given to us by nature itself. So fundamentally, they should match nature. And it seems like nature has dictated that there's this extra constant term. And when we do incorporate that, we get things that match quite neatly with the observations and produce a late-time accelerated expansion of the universe. So I've talked to you about our concordance cosmology. I'll talk to you a little bit about discordance cosmology. And this basically is to give you a flavor for, we're not taking, as astrophysicists, these things as given by a deity, they're given by nature, and not every puzzle has been solved. So I'll go over some perhaps alternatives to cold dark matter, and some perhaps alternatives to cosmological constant, to the cosmological constant, and then I'll close with how simulations are exploring both predictions in our concordance cosmology and convincing ourselves that that concordance cosmology is actually the right one by actively exploring scientific alternatives. So cold dark matter. Simulations aren't without problems, and here are 4 horsemen of the cold dark matter apocalypse, namely missing satellites, the cusp core problem, too big to fail, and the angular momentum bailout problem. And I'm not going to go into all of these in exquisite detail. I will mention that one called the angular momentum bailout problem is no longer considered a problem, and that goes to show that some things with increased observation quality, with increased simulation quality, some problems aren't problems for all time, they're just current problems. They go away. And I'll go over, in particular, the missing satellites problem. So that issue is that n-body simulations, simulations of cosmic structure formation, predict more satellites of a galaxy such as the Milky Way than we observe if you do dark matter simulations only. So some people said, well, maybe we don't understand gravitational physics. What if we modify general relativity or even Newtonian mechanics in a way such that we get that flat velocity curve without resorting to dark matter? And so far, none of these have held up in a cosmological simulation context. They produce more problems than they fix. Another alternative might be, well, what if dark matter behaves in a slightly different way? What if it has a slightly different velocity? What if the particle is slightly different? And people have managed to do simulations of cold dark matter, warm dark matter, and hot dark matter. And it's not necessarily important that we understand all the results of these simulations together, but you can heuristically see that in the hot dark matter simulation, it doesn't have as much of this filamentary structure that we observe in the universe itself. So it's quite clearly ruled out. Whereas the warm dark matter has less structure, and it's in these nodes that look a bit like neurons that galaxies themselves form. We see that in the warm dark matter situation, it has more potential of matching reality. And some papers indicate that it might solve some, but not all, of these issues, particularly in the one that I went into in detail, the missing satellites problem. A warm dark matter particle has a smearing effect on cosmic structure, so that means that fewer satellites are formed. However, since this doesn't fix all problems, and there's indication that just simulating dark matter physics alone is not enough, and I'll go into the increased physics that are being incorporated into modern simulations, cold dark matter is still the favored paradigm. However, physicists actively explore alternatives, and that's one of the joys of being a physicist and being a simulator, is that you can come up with an idea, calculate its expected effects roughly, and then actually simulate those expected effects and rule in or out your model. So some alternatives to this cosmological constant, and this I'll call the dragons of the cosmological constant instead of the four horsemen. First, there's the cosmological constant problem. So this is good news and bad news. The good news is that unlike dark matter, which isn't predicted by any of the best candidates of particle physics, namely it's not predicted by the standard model of particle physics, the cosmological constant is predicted. However, it is predicted to be much, much larger than the cosmological constant that we observe from nature itself. So there's a discrepancy of almost 100 orders of magnitude. And there's also a coincidence problem. Namely, this is the fact that the universe hasn't always been dominated by this accelerated expansion phase. Previously, the energy distribution that dominated were other components, such as matter or radiation. And it's only in the current epoch in which we happen to live as humans where the cosmological constant is beginning to dominate. So usually, when we assume that we're somewhere special in the universe, this is an incorrect assumption. So the coincidence problem leads us to think that perhaps we aren't at so much of a special place, and maybe think that maybe there could be another explanation. So two alternative explanations are, first, you could have some sort of scalar field permeating the universe, perhaps a different type of particle or field than those predicted by standard physics. Or here's a funny cartoon about how Einstein is wrong. I'm currently conducting an experiment which may prove Einstein wrong. Ooh, exciting. It's impossible to find a good sandwich in this town, said Einstein in 1947, and this was disproven. So this is just to say that, of course, Einstein wasn't right about everything, and it could be, as I mentioned before, that these equations aren't given by a deity, they're given by nature, and maybe they're more complicated in a way that is different than a cosmological constant. Perhaps it has more mathematical terms, functions of things rather than constants. And so these are two proposed alternatives that people, myself included, have explored actively in simulation. So far, it looks like the cosmological constant is the simplest explanation for the observations. However, it's a beautiful thing to be able to try out in toy universes different consequences and convince ourselves that that dark energy, that the cosmological constant is the correct explanation. OK. So one thing that I'll mention, I won't go into my research in detail, but if you try to work in a field to develop alternatives to the cosmological constant, because all our observations match it so well, you have to tweak the equations such that they match our observations on the cosmic scale and on the local scale very well. And often this is done via mathematical chameleon effect. Essentially, you design a mathematical function that hides its modifications of gravity locally and only comes to light in reproducing things such as the cosmological acceleration, as well as some additional observables, because of course you want, in the end, to be able to differentiate between your theories and alternatives at the observational level. Philosophically, if you can't actually scientifically differentiate between two theories, what difference do they actually have? So it remains to be seen whether any of these alternatives can slay the dragons, but to date, most physicists work with a concordance cosmology, and there is a community that explores alternatives, and most of that community remains convinced, nevertheless, of the concordance cosmology. So I've told you about some puzzles that physicists are working to address. What is the nature of dark matter? What is the nature of dark energy? What is causing cosmic inflation? Is it a cosmological constant? Is it something else? The horizon problem, the cosmological problem, and there are many more in astrophysics. I'll also give you a few other puzzles that I won't talk about in detail, but the reason why there's more matter than antimatter in our universe is unclear. How the first supermassive black holes formed, they formed very early after the Big Bang, and it's unclear how they were able to feed or grow so quickly. How stars actually explode at the fundamental level. We observe exploding stars all over the universe. What is producing our ultra-high energy cosmic rays that we observe, very high energetic particles that are observed on Earth. The unification of quantum mechanics and general relativity, and there are many more in astrophysics. And I mention these because we have a good understanding, but we're trying to explore the solution and the very nature of even those things that we think that we do understand. So some ways to address this. Historically, this is Einstein's notebook, and you might see some indication of the notation that we saw before. A physicist would calculate, a theoretical physicist would calculate. And then there would be people who looked at the stars themselves, and later we built Earth-based telescopes and also space-based telescopes. And there wasn't really anything in between. You were a theorist calculating, or you were an observer observing nature as it was, and you were trying to match these two. And I view supercomputing as something in between the two. So first, you are a theorist because you take your theories, you discretize them, you put them in a language that the computer can understand, and you simulate and evolve them forward. But you're also an observer in that you're generating huge data sets, observing those data sets, and creating predictions that can and should be verified by people who are looking at the universe directly. And the dream would be that your theories match the universe so well that you're convinced that they're right. And this is just an example of one supercomputer in the US. There are supercomputers all over the world. Many modern nation states have it as part of their scientific and national defense infrastructure. They're very fast. They're used largely, for a large part, physics in the academic community. Here, this supercomputer in Texas is called Stampede, and it's used 41% for physics. And one example use was to explore one of those unresolved questions that I said before, how stars actually explode, what is the supernova mechanism, how to better understand it. So now I'll go a little bit more into simulation details, how you might actually simulate the universe on a computer to try to address some of these questions. And in ancient times, Aristotle thought that there might be 4 elements: earth, fire, water, and air. perhaps a fifth element called quintessence. And I'll just use this as a little analogy of some select elements of astrophysical simulation. Of course, there can be different ingredients depending on what physical phenomenon you're trying to simulate, whether that's planet formation or whether that's structure at the cosmic scale, whether that's a supernova, a black hole, a single galaxy, clusters of galaxies, or clusters of other objects. And so here are some select elements. We have, of course, gravity, which would be simulated with n-body or numerical relativity equations. We have gas physics, which would be simulated with hydrodynamics. Essentially, we can model the non-dark matter component of our cosmic structure as a fluid. There's magnetic fields and photons, which would be modeled by the equations of radiation and magnetohydrodynamics. And there's subgrid physics that is perhaps below our resolution, but we try to model heuristically to match observations in the best way possible. And that could be, depending on the simulation, what is below your resolution will change. That could be stars, that could be black holes, that could be cooling, chemistry, physics, et cetera. And I'll actually briefly flash the equations here, some of them. We won't go into detail, but it just gives you a taste. That's n-body and numerical relativity equations. We have the Euler equations for gas physics. We have the equivalent for magnetohydrodynamics. We have a radiation transport equation. And we have each researcher, depending on the equation or the type of physics they're trying to model, may have a different set of subgrid models. So for some problems, gravity may dominate, in which case you can say within your error bars, you can just include one portion of the equations and ignore the others. However, as we're always trying to refine our understanding, we're always trying to incorporate as much of the physics of the universe as we can afford to on our supercomputers. And we've had progressing abilities here. And I'll show you another plot. This should be my last plot here. So here, on the y-axis, I have the resolution of the simulation. On the x-axis, I have over time. And then here are various numerical schemes. So there are different ways of discretizing, of representing these equations computationally. And different sorts of physics. Some include just cooling and star formation. Others include stellar feedback and black hole feedback on top of the basic n-body and gas dynamic equations. And then here we have many academic astrophysicists. And the takeaway from this plot is that there's more resolution and more physics that we're able to address over time. And this is allowing us to have more confidence in our simulations and make new and novel predictions in areas where we were previously not able to simulate. So the higher resolution you have, if you're simulating on the cosmic scale, that basically means if you can imagine the universe as pixels, it used to be that the universe would look more like an 8-bit game, where each individual component in our simulation was to very poor resolution. And now we're able to simulate things with the resolution that we're able to see not quite the hair on the black hole. It's a joke. Black holes are thought to have no hair. You won't see the hair on the black hole, but we're able to see in more exquisite detail the actual nature of the effect of our equations. OK, so I'm going to close with some amazing movies. And I'll start out at a smaller scale, and then we'll get up to the scale of the universe of some of these examples of equations in action. So these are Black Holes Annihilating, done by my collaborator and colleague, Christian Reiswig, who's actually now here in Berlin at the Albert Einstein Institute. You can make a pilgrimage to see him. And here are, hopefully if the movie starts, here are two black holes that are being simulated. And we'll see that they orbit each other, and they'll eventually merge. And the equations of general relativity predict a phenomenon called gravitational waves, radiation essentially from gravity. And there are actual detectors being built by international collaborations to observe these gravitational waves. And simulations such as this actually predict the properties of these waves so that these extremely expensive experiments that will give us a new telescope of observing the universe in the gravitational wave spectrum are best able to observe and calculate their observation program. Next, I'll go into a little greater of a simulation. So this is actually a problem that I've started working with as well with Christian, and this is the issue of perhaps, I mentioned before that one of the puzzles of modern physics is how did the first supermassive black holes form? And one candidate is perhaps we have a supermassive star to begin with. However, these supermassive stars are quite difficult to form because if you have a large gas cloud, it more readily wants to form many smaller objects. So you have to have unique conditions under which these supermassive stars could form, and perhaps we might have those conditions in the very early universe, exactly when we need these stars to potentially form supermassive black holes. So here's a simulation of these, a supermassive star actually collapsing and forming a black hole. And we're able to predict properties and eventually predict in certain situations that these stars could explode and we would observe those explosions and the nature of those observations. Now I'm going to go up in scale, and this is by a colleague, Volker Springel, who's at Heidelberg here in Germany. There's a lot of great computational astrophysics going on here in Germany, in Europe. Did my PhD at the University of Zurich, which also has a fantastic computational astrophysics group. And here's a single galaxy forming. And the very first galaxy formation simulations didn't necessarily form a beautiful spiral structure, but we saw that by adding increased resolution, by adding more exquisite physics, we were able to observe and predict properties that galaxies like our very own Milky Way might have. I find this movie extremely beautiful. And something interesting to note is that these are, the time is given in mega years, so not just a year, but mega years. OK, so here's dark matter on cosmological scales. So this is a dark matter-only simulation, and as I mentioned before, if you have a problem for which gravitational physics dominates, and since the majority of physical matter in the universe is, in fact, composed of dark matter, our own galaxy has 100 times more dark matter than baryonic matter. It is, in fact, for many universal questions, such as the nature of cosmic structure, to match observations, it's very well predicted by dark matter physics alone. And this is from the Millennium simulation, which was done around the Millennium, and it has since been done in increased resolution by the same group with the Millennium 2 run, et cetera. And we can see a tour of a universe very much like our own. And the large-scale properties, the distribution of where we expect galaxies to be, of matter in the universe, matches very well with observations. And finally, I have a simulation on the cosmic scale that incorporates many of the ingredients of, most of the ingredients of that Earth, water, air, and fire diagram I showed you before. Namely, this has dark matter and body physics, it has hydrodynamics, it has many models of star formation as accurately as possible, gas cooling, it has black hole physics. So this simulation is done by the illustrious collaboration out of Harvard. And we can see just how beautiful our universe is and see how we might in fact, simulate it in a supercomputer. OK, so just to recap, we started out with the initial conditions. We simulated the evolution of those initial conditions of that cosmic microwave background radiation, the density given by that. with a variety of physical methods. And we have predictions to compare to near-present-day observations. And this work is done by a variety of physicists throughout the world and helps to inform our understanding of the universe on a philosophical and human level, our ability to create and design experiments and observations in a way that's as efficient as possible, and actually probing these fundamental conditions, not randomly looking, but looking in a very efficient way. What are the questions that we can ask to spend our telescope, our scientific budget in the most ideal manner possible? And finally, these large-scale supercomputing techniques have really prototyped the way for many other fields. You saw that 41% of supercomputing time is physicists and natural sciences. Another big portion is chemists doing computational chemistry. Both these areas have prototyped and developed algorithms that are now extending into biology, and there are many computational biologists and computational neuroscientists that are using techniques that we were really forced to use very early on to address problems in astrophysics that we now have access to and are also being forced to use in problems such as biology, et cetera. So I'd like to thank you very much. And I'll leave you with that, and I'll take a few questions. Thank you.
Are there any questions? I come around, just raise your hand. Oh, yeah.
What role plays art and artistic expression in the construction of these visualizations?
So I think there's a great deal that art can play, particularly if you look at multimodal data that comes from a variety of different sources. From the astrophysics scale, you might have, from actual observations, data from different wavelengths that the human eye can't even perceive. And so it's a manner of art and usability to construct an image that a scientist can make the most sense of in this data that they're not even able to see with their eye. In addition, in these cosmological simulations, you might have data that comes from the n-body component, the dark matter physics, the baryonic physics, and you might want to represent this in the same visualization in a way that a scientist can see, and that a person or a funder or the public can appreciate the effects. And I think there's a great deal of both art and also usability in that you want to be able to actually pick out the features that are important and not highlight things that are spurious for the scientist.
Are there any more? Oh, yeah, over here.
Yeah, I have a question. I'm not quite sure how to phrase this because I don't know enough about it, but I was interested in the way you highlighted the sort of Discordian aspect, and I think, yeah, it seems like the standard model is not as standard as it might seem. So, regarding the more outlandish cosmology or physics, maybe, I don't know, something like the holographic principle, the idea of a holographic universe, something like that, which sounds so outlandish. From your point of view, is it conceivable that something is going to happen on a massive scale, like for gravitation, supersymmetry, something like that, or even that you say at some point you'll have the holographic principle as a kind of standard model? I mean, is that conceivable that the foundations aren't as standard as?
I would say two things on that question. One, that certainly we don't understand how quantum mechanics and general relativity unify. And I think that because we don't understand that we can't necessarily expect exactly what the solution will be. What we can say historically is that even when Newtonian physics was usurped by general relativity, Newtonian physics falls out of general relativity if you do the math at certain energy scales. So we can say that probably our theories that are currently being used, since they match so well with observations, they will still fall out of a higher level theory. It just will be that the higher level theory will allow us greater understanding and perhaps to predict things that we're not able to with our current theories. So I don't have perfect intuition as to what that might be. I would say I would not be surprised if in the next 40 years we find something fundamentally new. What that fundamentally new thing will be, I'm not sure about, but that even so, it's very useful to work with our current theories, our current understanding to make predictions, because those will match at some level the observations.
Yeah, over here.
Thanks for your very nice talk and the wonderful pictures. Can simulations now tell us what is going to be the fate of the universe? Is it already infinite? Is it going to be infinite?
So our current understanding is that the universe is already infinite, and that because it's accelerating in its expansion, and because it's flat, that the geometry of the universe isn't curved back on itself, that it will continue in this accelerated expansion for the rest of time. And eventually, galaxies will become farther and farther from each other, and eventually there'll be sort of a heat death of the universe where everything just cools down. And it doesn't look like it's going to come back together. But that time scale is astronomically huge. It's orders of magnitude larger than the universe has even been in existence to date.
Any more questions? Oh, yeah. Wait.
Thank you. I would like to thank you for your talk. Sorry about that. Move the microphone. I like to ask every astrophysicist I meet a single question, and I hope you indulge me. Douglas Adams wrote once that if the universe were to be understood completely, it will be replaced by something so outlandish that it defies understanding. Would you agree with that statement?
That's a very subtle statement, and as usual, Douglas Adams and many science fiction authors, Cory Doctorow included, have excellent things to teach us about our reality, our physics, our politics. To get to the question itself, I would say my intuition says that it would be very difficult to simulate the entire universe with the entire universe. So to me, simulation is a proof of understanding almost. But if we can't simulate the universe with the universe, we may never be able to truly understand the universe. So I kind of feel like we'll never reach that state. I don't know about if we reach that state, if it would be replaced by something else. But my intuition would say that we'll never be able to completely understand things.
There's time for more questions. If you have questions, just raise your hands. Oh yeah, over here.
Thank you all for the great questions, by the way. It's an honor to be here.
Well, it's nice to have you here. You just said the universe is flat. I didn't know there was consensus on this. Is there a consensus?
There is a consensus, yeah. And that basically comes from, there are many observations that might show that, but you can calculate that from the structure of the cosmic microwave background radiation. It would give you either be lumpier or less lumpy if the universe wasn't exactly flat. So essentially, we can use that to calculate how much of the energy balance there should be in the universe and the component of which the cosmological constant is a member of.
Wir haben da drüben eine Frage.
Ja, danke. Hi, Christine. Here.
Hi.
Hi. Thank you for that. It's mind-blowing. It blew my mind. My question is, you know, when it starts somewhere as a nutshell and exploded into what it is now, flat or whatever, concave, doesn't matter really, but what has been or what is around this nutshell? You know, my mind kind of goes haywire when I think about, you know, it started as something, but what's around it? Where does it expand to? And is there anything, you know, I heard Stephen Hawking talk about it, but, you know.
So I feel like every physicist has a different way of mentally understanding this. It's a lot easier to understand in mathematics than it is to try to incorporate into an everyday understanding. But as I mentioned before, general relativity gives a relationship between geometry and matter. And so how I like to think of it is that the coordinates on which we're operating, if you imagine a sheet of graph paper that has a bunch of lines in it, now if you shrink the size of the squares in your graph paper from large squares to smaller squares to smaller squares to smaller squares, nothing really fundamentally changes if you have an infinite sheet of graph paper and you're only allowed to plot at those little points. Then when you shrink the infinite sheet, everything gets closer and closer together until the point where the graph paper, you can't even see the squares anymore. It's all at one point. But that point is still infinite in your conception. So when the Big Bang happened, what happens is that point expands into those squares that we see today, and those squares are getting bigger and bigger of space-time, and now they're in fact accelerating at the rate that they're getting bigger. So that's how I like to visualize it.
Any more questions?
I'll be around for the rest of the day and the conference, so feel free to come chat me up. And I'd love to hear about what you guys are all up to. Been really enjoying the conference, so thanks a lot.
Christine, thank you very much.